Anyone here old enough to remember this? This is Turbo Pascal. It's actually Turbo Pascal 2.0, but Turbo Pascal 1.0 turns 35 years old today, and that was the first product that I worked on. Here's a later screen grab of Turbo Pascal 5.0, Delphi, that Christoph mentioned. I'm sure some of you would probably know C# that I also worked on. But today I'm here to talk about TypeScript. And as you can tell, I obviously have a fascination with programming languages and development environments, and in particular, the symbiosis between the two. And TypeScript is no exception. The story of TypeScript starts about 8 years ago, late 2010, early 2011. And at that time, there was sort of this perfect storm happening on the web. We were moving from a world that was very homogeneous, sort of dominated by Windows desktops, to a very heterogeneous world of devices in all sorts of different form factors and operating systems. And so cross-platform was really becoming super important. And at the same time also, JavaScript VMs were getting way, way better. I mean, already at that time, we were at least seeing a 10x improvement from the great work that Google did with V8 and Mozilla and even Microsoft with our Chakra engine. And it was sort of on this steady upward march of better and better performance. And ECMAScript 5 had been ratified, and HTML5 was on the verge, and so it was becoming not just necessary, but also possible to write real-world apps in the browser. And certainly, history has borne this out. If you look at, shortly after we started with TypeScript, JavaScript jumped into the #1 spot of most popular programming languages and traded with Java and has pretty much stayed there ever since. So it's with this backdrop that in 2010, this group of people came to the developer group and asked whether we would consider productizing a project called Script#. Now, at the time, I was working on the C# programming language, and Script# was this tool that allows you to cross-compile C# to JavaScript. In a sense, just treating JavaScript as an IL, right? And I was like, well, why would you want to do that? And this tool was being used internally by the Outlook.com team, but Google had a similar toolkit called GWT that they were using for a bunch of their properties. And so I got curious about what the reason was. And it turned out, that there are a couple of reasons. We all know that JavaScript has issues, and at the time it had way more issues than it does now. It didn't have classes, it didn't have modules, and it didn't have a type system that allows you to describe and document your code, which is super helpful when you're working in big teams and when you want to statically check your program before you deploy it. And also, a lot of the tools at the time for JavaScript development kind of looked like this. There was just nothing, no help, no colorization, no statement completion, no code navigation. And again, part of the reason was that there is no type system in the language that can inform these tools, and you need all of that information in order to build great tools. So that was sort of a genesis moment for us. This is where we go, well, gosh, we're never going to be best of breed by targeting JavaScript from C# or some other language. What if we instead could work on fixing the problems that we're seeing here, like adding a type system that's optional, adding classes, modules, and so forth. And that really sort of was the genesis of TypeScript. So TypeScript starts with JavaScript, as I'm sure a lot of you know, to which we then add a static type system plus missing features, or at least they were at the time, like classes and modules. And then on top of that, we build great tooling. But then when you compile your code, you're just left, again, with plain old JavaScript. So there's really no notion of any of this having existed other than at development time. So that's, in a nutshell, TypeScript. We shipped it in 6 years ago, was the first public release. And here are sort of here's the value system that we live by. We are fully open source and open development. We are on GitHub. The team is there every day. We try to closely track the ECMAScript standard, so we don't see it as our job to add new features in the core language, but rather we want to innovate in the type system. That's sort of our purview, but that is a development time only thing. We strive to build best-of-breed tooling and continually lower the barrier to entry and listen to our community. This is the group of people that build the product, most of them in Redmond. What I wanted to do now is try to dive in a little bit and talk a little bit about the type system, because that's sort of like the crown jewels of TypeScript. That's what makes it different. Our type system has a whole bunch of interesting attributes that I've never seen in other type systems. I've listed all of them here, but rather than read them to you here, I'm going to try to go through a series of illustrations of what this means. And so, starting with this notion that types are erasable. Here's a piece of TypeScript where we declare a person type, and then we annotate our parameter called person on greeting, and we annotate our user variable with that type. And once we do that, then our tool, our IDE, knows what's going on and can give us statement completion. It knows what the properties of that type are. It can check that you're not accessing other properties and so forth. But when you compile, all of that stuff just evaporates. So there's actually no notion of types ever having existed in the final code, and this is what you actually end up running, and it's just plain old JavaScript. In fact, you could feed this to the TypeScript compiler, because TypeScript is a superset, so this is just TypeScript with no type annotations. And if you do, then we can actually infer types in a lot of cases. So inference is super important to us, and in a lot of cases, you really don't have to write type annotations. Although, if you do feed this program, for the person parameter on greeting, we just infer the type any, which means it could be anything. And now you might go, well, gosh, listen, you could infer the type of user, and you're calling greeting with user. Couldn't you infer what the type of person is from that then? Some type systems do that. That's like non-local type inference, where you're inferring from calls. But the problem is, imagine that call sat very far away in a different module, and all of a sudden started passing some different parameters, and then all of a sudden over here we would infer different types for the parameter. That's sort of like this spooky action at a distance, which in Haskell and ML can sometimes be very odd, and we strive to not do that. So any inference we do, we keep it local. Our type system is structural. Here's an example. Again, if you look at the type annotation on person in the first function there, you see that we haven't even given it a name. We've just said it's something that has a name property. And then it doesn't really matter how you get that name property. You could get it by being an instance of a class that has it, or you could write an object literal, or a number of other ways. What matters here is the structure, just the fact that you have that property. This is distinctly different from languages like, say, C# or Java, where you would have to declare an interface called thing with name, and then you would have to have your person class implement that interface. And only if it implements that interface can you actually pass it around. So interoperability in those languages is much, much harder. There's much more friction, where JavaScript actually is duck typed, right? And really, our structural type system is really just a static formalization of duck typing, and that is how JavaScript works. We have a generic type system, which means you can declare things like this here, which is a strongly typed node in a tree, where P is the type of the parent pointer. And because we're structural, if you have two types that are identical in structure, they need to be compatible with each other. So let's say I have a node of something and an item of something, and I try to assign one to the other. In a nominal type system, that would be an error because it is not the same type. But in a structural type system, it should be okay, which means we're going to say, node of null equals, is node of null assignable to item of null? Then we look at a structure. Well, yes, they both have a data property. Yes, they have a parent property, which is going to be of type null. And then they have children, which is of type node of null. Now let's compare those. Off we go, compare, yes, yes, yes. Now node of null, node of null. And it's turtles all the way down. This is very hard to implement. The nominal type systems are a lot simpler, but in structural type systems, you are staring into the recursive abyss all the time, and you need to find ways to not go off and do infinite amounts of work. And so we have something that we affectionately call the turtle cutoff in the compiler, where we say after 5 turtles, maybe we should look at the rest of the types, and if all of that works out, then we're just going to say it's okay with a high degree of certainty, because it is not possible to really truly tell. Union types are another thing that we have here. The ability to annotate a parameter with being either string or number or Boolean. And then when you couple that with control flow analysis, then wonderful things come out of it. Here, for example, we can infer that the type of X inside that if statement is just string, because what the guard that went before it, we can narrow the union type down to just string. And then following the assignment, it becomes a number, and then that means at the bottom we have number or Boolean. Now that's super handy when it comes to checking for null and undefined, because in strict mode in TypeScript, null and undefined are separate types. And so if you guard with X equal to null and return, then we know through our control flow analyzer that X is not null in the rest of the function because it's been guarded. A lot of people say, I don't like TypeScript. It's all about programming. It's all about OOP, and we don't want OOP. We want functional programming. Well, it turns out that we are actually really great at a bunch of functional paradigms. Here, for example, is what we call a discriminated union type that has a kind property, and it can be one of 3 different kinds. And then in the area function, when you are in each of the different cases, we can narrow down to the appropriate case and only make those properties accessible. And we can also know that you've handled all the cases, which means that the bottom of the switch statement is unreachable, and therefore the implied undefined that the function would return otherwise isn't actually there, and therefore the inferred return type is number, not number or undefined. And so there's a whole bunch of intelligent stuff that happens here, but this is just pure old JavaScript. But when you squint, this is just like an algebraic data type in one of the functional programming languages like Haskell and ML, and a lot of the same techniques like exhaustiveness checking and whatever become possible with TypeScript. Indeed, JavaScript is this interesting language where you can do things that don't even exist in other programming languages, like have stringly typed APIs where you pass property names as strings. And through some of the type system operators that we have, like keyof and index access types, the T sub k there, we can actually strongly type these patterns and give you an error on the last line here, because we know that the string literal you're passing in is supposed to be a property name in the object that you're passing in. In fact, we have a bunch of esoteric types that we've dreamt up just to match JavaScript's capabilities, like lookup and map types, and the latest one is conditional types. In fact, someone actually proved that our type system is Turing complete. You can do computation in the type system. If you guys want to see something crazy, go look at that particular issue. It's still up on GitHub. Another thing that we have is strict mode. It's sort of a dilemma for us, because when we evolved the type checker, we are in a sense breaking your build every time we release, because we get better at checking and we might find new errors that we didn't find before, and therefore your build is broken. Now, in order to handle that, we allow you to opt into features individually, or you can opt into strict mode, in which case you're saying, yes, I want maximum type checking at all time, and that just enables a whole family of stricter checks. Another thing I wanted to talk about that's special about TypeScript is this notion of using the compiler as a service. Compilers traditionally were these things where, in comes input files and out goes output files, and magic happens in the middle that only the compiler writers understand. But in reality, today, compilers need to be opened up and become APIs, because that is what enables all of these wonderful features that we expect to have in our IDEs. And indeed, the TypeScript compiler has an entire API on it where you can use the parser, the type checker, and so forth, and embed it in your own tools. And tools indeed do that, like TS-lint and Webpack and all sorts of other tools. Also, we work really hard to make it easy to embed in different editors. So Visual Studio Code, for example, Sublime Text, Vim, Emacs, all have plugins that allow you to use TypeScript in there. And in order to make them as easy as possible, we actually have a thing called TypeScript Server that runs as a separate process that the editor extension can talk to through a JSON protocol. And then all the magic happens over in that server, and the protocol just tells the server what editing actions happened. So another thing that we need to really focus on is performance. There's sort of this magic number for IDEs, 250 milliseconds. If it takes longer than that when you press dot, then users get irritated. So that's a hard problem to solve. If you have a 100,000 line program and the user is typing and presses dot, and now in 250 milliseconds you have to somehow figure out what comes here. And obviously you can't compile all 100,000 lines and do that. Here's an example of the responsiveness. You see when I type dot on program here, this is a 100,000 line program. This is the TypeScript compiler and language service itself. And you see how we are probably sub 100 milliseconds in response here, even though technically you could reference anything from that 100,000 line program right there. Now the way we do that is when we're running this TypeScript server, when the editor extension talks to it, let's say it tells it that I've loaded a file. Then we go parse that file into a syntax tree. Then we analyze that syntax tree to see what this file references through imports, for example, and then we can build a full closure of everything that we need to know and hold on to it in memory because we're sitting as a service out there. Now, let's say the user presses dot and we need to know something about what's in scope here. Then we need to build symbol tables for each of these guys. Then we can build a global symbol table, and now we can start to answer the question. But the minute we answer the question, the user actually, as a result of pressing dot, modifies a file, and now he made our assumptions invalid. And the program, by the way, is also broken because there's an error because he hasn't actually typed what comes after. So now we have modified a program and it's broken, yet in 250 milliseconds we need to figure out what comes next. Now, what we do know, though, is that we can clear out the information just for that file. And then we can incrementally recompute it and reconstitute it and then answer the question. And even in the process of incrementally building, we can use some of the old data structures that we have parts of the syntax trees that weren't modified. But you'll note that if we had 100 files here, 99 of them did not get modified. And so we saved ourselves a bunch of time. And so there's a whole bunch of techniques that you have to do when you build compilers this way. And these are techniques that you're not really taught in school. This is something that you learn by doing. But you can see it all in our GitHub repo. It's an interesting piece of code. In terms of community, there's this fantastic website or GitHub site out there called Definitely Type, where the community is collecting type information for JavaScript programming on the web. It just this year moved into the top 10 most active repositories on GitHub. So it's up there like along with Linux and React and like some really big players. And it goes to show how much activity there is here. And basically this has turned into a treasure trove of information because it really documents in a uniform manner how all of the frameworks on the web work. And I'll show you an example of how we can put that to good use. We also try to really work with all the other tools that are out there in Babel. The latest version of Babel now supports TypeScript. And TypeScript, well, you could always use it just as a type checker. And so that means now that React is within reach, for a lot of users. They can use TypeScript and Babel. That's becoming very popular. And we see ourselves sort of as the Switzerland of frameworks. We don't really try to cater to one particular framework. We work with the main engineering groups of all of these different frameworks and make sure that we have all the right features handled for them. So you might say, but I don't like types. It's like they get in my way. I like parachuting. I like bungee jumping. I just want to write myself some code. And I actually seriously, I can understand that. There are scenarios where it's just maybe not worth it for you. But it turns out that we can actually still deliver a bunch of value because TypeScript is a superset of JavaScript, which means JavaScript is a subset of TypeScript, which means we can actually use the TypeScript language service to analyze JavaScript. It's just like JavaScript with no annotations, right? And so here is a little example of me starting a completely blank project. I have installed Lodash as a node module, but that's all I've done. And now I start a blank file, and I just start typing. This is in Visual Studio Code, import underbar from, and then see we get statement completion on Lodash. But now if I say let x equals underbar dot, then notice statement completion. This came because we could auto-provision from definitely typed and grabbed all the type information from there. And we could actually now put that to good use and show you what's possible to type or to write here, even though you haven't said any type annotations. Now, if you say go to definition, you can see that we actually go into the declaration file for Lodash on that particular identifier. Also, you might have, say, JS doc annotations in your code, and we can actually scrape those and treat them as type annotations, right? So here's a function that just takes some s. But now when I say s dot, you'll see that I get statement completion because we scraped the JS doc annotation and we know what the properties are on string. But if I call it, we don't give you errors because, hey, this is JavaScript. I mean, it's possible. And likewise, if you spell this wrong up there, we also don't give you an error. However, you can opt into what we call TS check, which is basically go check it. And if you're absolutely sure there's an error, then show us that error. And also, in here, you'll see that now you can actually use refactorings to go do the rename and whatever. And so we can do a lot without type annotations. And you can get a lot of the benefits from TypeScript without actually ever really using it, which I think is pretty cool. Okay, final thing I wanted to show is just a slide that made me, or a graph that made me happy here recently. TypeScript has now moved into the 7th spot of the top languages on GitHub, and I'm of course a little bit ambivalent about who we have to beat next to move up, but but nonetheless, this is great. So this wouldn't have happened without your support. I know, actually by show of hands, how many of you use TypeScript currently? Oh my God, that warms my heart. I want to give you a heartfelt thank you. And I also want to say that for those of you who haven't yet used it, give it a shot. I think it might actually make you more productive as programmers. Thank you.